Hey, good morning, neighbors. This is going to be hopefully a quick one on Geiger counters and how you know your Geiger counter. If you're considering buying one, if you're looking at one, or even wondering about your own, there's three very specific elements to Geiger counters that are fundamental to them all. First one is the detector tube. What type of tube is it? This defines what radiation the detector is capable of seeing. That is a detector characterization sheet, detector specification sheet, and if it's not available for the detector, then something is wrong. And sometimes they're very hard to find. Both the detector ID, maker and part number, and the data sheets around those. That matters because the detector, again, it's got really two characteristics. What can it see? And how does it see it? It needs a high voltage source, very stable, and a sampling circuit that sits on top of that high voltage to be able to count little counts on top of a pulse. So the tube also has, in order to get the characteristics built, there was a specific voltage and other attributes set on the sampling circuit for that tube, because the circuit has to be matched to the tube type because the speed of what we're doing, there's something called a quench circuit where the detector has to be quenched back down to its base voltage, and then as the next counts come in, it sees a count, quench, sees a count, quench. So that rate is defined by the electronics capability that's attached to the detector. So that's that tiny little high voltage power supply circuit. Is that power supply stable? Does it have good characteristics? Is it temperature compensated? So if you go look at, as example, the Safecast Geiger counter, it's using an IMI power supply, which is a noted supplier of Geiger counters. So that power supply has some interesting features about it, but it is one of the keys to that instrument's stability, and it actually does work very well. All of my tests, user tests for interference for that meter, is fantastic. It doesn't respond to EMI or RFI in any way I've been able to detect, or it's not photosensitive. So if it's out in the sun, it doesn't respond to the sun. So those types of things can matter and are characteristics of the tube. On top of that, you put the tube inside of a case. If that case shields any of the elements from the detector circuit, from the tube and the detector circuit, then the tube is not going to see it. So is the housing around that detector open so that it's being used as it was characterized in a lab? And the odds are no. And the odds are, for your instrument, that characterization wasn't redone in the full configuration of the meter, because you can assume some things if you know about the meter. If you know about alpha beta blocking by almost anything, then a fully covered detector is probably not going to see alpha very well, no matter the tube characteristics, and other tubes won't see it at all. So the tube type, the voltage, the specific detector circuit. So I said the tube has a quench on it. So basically when you use a number, it's not the right one. It depends on the tube, the electronics, and the person's knowledge. So that quench time, it happens at a set frequency based upon the detector, the CPU doing the data logging, whatever's doing the data logging. I'm using a sophisticated meter example because old meters just used a summing capacitor for this work. New meters are better, different, better. So that detector circuit, the counting circuit, has to be able to match the frequency of the quench timing on the detector. And if this all got complicated, yes, it is. If you want a good detector, if you want to understand and have confidence what the detector is telling you about. So again, I work in counts because converting the detector into any other reading has too many errors. You're doing multivariant calculus at this point in order to get to where we're trying to get to. So all of the variables matter: temperature, background. It takes a long time to get good readings and test these meters out. So like EMI testing, you go stand by a huge transformer set for an hour, and then you walk away from it and you're looking to see if the average for an area raised up whatever percentage. If you can see it on the graph of your meter, then that meter is seeing some type of something in that area, and you can pretty safely assume it's EMI from a big transformer set, electromotive interference. RFI, you would get radio frequency interference. You would get from cell towers. You can do the same thing. Go stand by a cell tower for half an hour, logging your data, and then go back home and look at it and see if you've got a 2-point average increase because of RFI radiation. So that, again, cell towers, microwave oven, those are good things to test. That's high frequency energies, and if your meter will respond to it. Now, high frequency can be, EMI radiation can affect the detector, or it can affect that high voltage power supply circuit, or even the counting circuit, but that's a lot harder to do. So it would take a big pulse to affect the overall electronics. You're affecting that super sensitive tube inside the meter. So again, 3 things: detector type, that defines the physical abilities of what the detector can see, and its characteristics are defined, tested, using a very specific detector type circuit, which is optimized against the tube's capabilities, to put it one way. So there you go. There's a quick 7 minutes on what's inside a Geiger counter, and a few ways you can test how things might interfere with it. But all of these things matter to trust your readings and to know what your readings are, and to speak to more than just the Sievert's reading, to speak to why you question how accurate the Sievert's reading is. So, hey, peace out. Be good.